Welcome back, everyone, to the deep dive. We see graphs everywhere, right? I mean,
Right.
textbooks, online courses, even news articles,
hmm
especially when they're trying to explain something, well, in science or social science, whatever. We just kind of assume that they're going to make this, uh, you know, complicated stuff easier to get.
Yeah, I think we see these visuals and we just think, oh, okay, this is going to be, like a shortcut to knowledge. And in a lot of ways, they are, but the research actually suggests that there's a lot more going on when we try to understand them than we might realize.
Totally. So to really get to the bottom of why some graphs just click and others just like leave us totally confused, we've been looking at this super interesting study, Review of Graph Comprehension Research, Implications for Instruction by Shaw and Huffner.
hmm
And our mission today is to really unpack what they found so you can become, well, like a total graph reading ninja.
That's the goal.
We're going to look at why some designs work better than others, how our own background and knowledge comes into play, and, maybe walk away with some practical tools for understanding this world of visual data. So let's start with the basics. Why are graphs so important in learning, and where do we often, trip up?
Well, Shaw and Huffner point out that graphs are absolutely everywhere in education. They're used to show everything from, math equations to patterns and social trends to scientific theories.
Right.
And I mean, they're not just in textbooks, they're in a lot of these digital learning tools we see now.
Makes sense.
I mean, if you're trying to learn about anything quantitative or scientific, you're going to see a graph as part of the explanation.
Yeah, I mean, the thought is, as backed up by folks like McDonald Ross, Tversky, and Wynn, that graphs just like take all these complicated numbers and make them easy to like visually grasp.
Yeah.
And visual aids in general, as pointed out by Larkin and Simon Pinker, can be really powerful for like directly representing a concept.
Right, right. But here's the thing, and maybe you've experienced this like we were saying before. Despite that idea of clarity, it turns out that understanding graphs can be, surprisingly difficult and prone to errors, as researchers like Bell and John Veer and Carpenter and Shaw found. We use them all the time, but we make these like systematic mistakes when we're trying to figure out what they're actually saying, especially when the graph itself isn't directly giving us the conclusion.
It's almost like sometimes the most important part of the story isn't the actual numbers themselves, but it's those like relationships and trends between them. And that's where things can get a little, tricky.
Right, exactly. And to show this, Shaw and Huffner actually talk about this really interesting example from a U.S. history textbook. It's about the trend of urbanization leading up to the Civil War. There's this bar graph showing the urban and rural populations in the North and South from 1820 to 1860.
Okay.
Now, the authors wanted to show that the North was becoming increasingly more urban, while the South was staying mostly rural.
Okay, so what was the problem? What did people actually see in the graph?
So instead of looking at the rate of each region urbanizing, which is what the authors wanted to show, most people just like compared the size of each population group. Urban North, urban South, rural South at different points in time. They were like just looking at which bar was tallest in a given year rather than seeing how the urban population changed compared to the rural population within each region over time. The way the graph was first designed just didn't make that message super clear.
But the cool thing is, when the researchers just took that same data and represented it in a way that made those trends much more obvious, like showing the percentage of the population that was rural in each region, the intended message just like, bam, it became way clearer. It's really amazing how, like, the way we visualize the data really affects how we understand it.
Yeah, and it makes the point that making sense of a graph isn't just passively looking at it. There are actual processes we go through. Research by Burton, Carpenter, and Shaw, Cleveland and McGill, Coslin, and others point to these three core stages when we're trying to make sense of a graph.
Okay, so let's break those down. The first one, encoding the visual array. What happens there?
So that's where your eyes are really taking in the graph, identifying the key visual elements. Is there a curving line, different bar heights, pie chart slices, all those basic building blocks? And Shaw and Huffner point out that, the actual visual characteristics can have a big impact on how accurately we even perceive this basic information.
So even something like whether it's a bar graph or a pie chart can actually change how well we like take in that visual data in the first place.
Exactly. For example, Cleveland and McGill found that we're better at comparing absolute values if they're shown as the length of bars, not the area of slices in a pie chart. Our brains just seem to be better at judging that kind of like linear extent.
Yeah.
Then there's the way information is grouped. Carpenter and Shaw, and also Shaw and colleagues, showed that connecting data points with a line makes us see them as more related, like a single gestalt whole. Basically, your brain tries to group them into one idea. It's different if it's just unconnected bars.
That makes sense. If there's a line, your brain's going to be like, oh, this is all connected.
Exactly. So once we've, taken in those features, what's the next step in really getting what the graph means?
Right.
Well, the next step is what we call relating these visual features to conceptual relations. So this is where we start to infer meaning from what we see. Like if we see a curving line getting steeper, we might think, okay, that's acceleration or a fast rate of change. And our experiences with graphs come into play here. Pinker talks about this in terms of graph schema. It's basically your brain's template for understanding graphs.
Mhm.
What do the axes mean? What do trends usually look like? Those kinds of things.
So like if I've seen enough graphs in my life, I might just automatically know that like an upward line generally means an increase on that vertical axis.
Exactly. It's kind of like a visual vocabulary we build up over time. But here's a really interesting point. Shaw and Carpenter in 1995 did this study where people could remember the visual features of line graphs, like how far apart the lines were, but they didn't always get what those differences meant in terms of the actual numbers. Like they couldn't always recognize the same data when it was shown a bit differently.
It's almost like, knowing the words in a language, but not understanding the grammar, right?
Yes.
You can see the pieces, but you don't really get what they mean together.
Exactly, yeah. And then you've got Tversky and Koslin who point out that some of these connections are easier because they're based on our real-world experiences. Think about it. If you see a taller stack of things, you just know there's more stuff. Vertically oriented bars in a graph use that same idea.
It makes sense. All right, so we've taken in the visuals, we've started to connect them to like concepts. What's the last piece of that?
Determining the referent of quantified concepts. This is all about connecting those labels on the graph. Things like population, rural, south, whatever the axes are labeled, to the visual information. So it's about really understanding what those visuals are actually showing us.
And this is where our own like existing knowledge or even what we think the graph should be showing can really mess things up.
Exactly. Like Shaw and Shellhammer found that what we already know about the topic can totally change how we see those labels and the data. And Shaw herself has shown how our expectations, affect our interpretation. On top of that, Lanehart and colleagues and others have seen that younger students sometimes struggle with this kind of abstract way of showing information. They tend to see graphs as like literal pictures of a situation, not as ways to show relationships between numbers.
Like that classic example of the race car speed graph, where a kid might think the graph is showing the actual hills the race car is going over.
Exactly, yeah. So these three processes, encoding, relating features to concepts, and understanding the reference, they're all linked and are affected by the graph itself and our own knowledge about graphs and what they're about.
It's like I can look at a graph and I can see the lines and the bars, but I don't actually get what they mean. That's probably a breakdown somewhere in those stages, right?
Yeah, exactly. Like the visual part is there, but you haven't made the connections.
Right. So let's talk more about the actual graph itself. What can creators do, design-wise, to make a graph easier or harder for us to get?
Okay, so this is where things get really practical. And a big takeaway, as pointed out by Carswell and Wickens and Simkin and Hasty, is that there's no one best type of graph. The best choice really depends on what you want the person looking at it to be able to do with the information. It's called the proximity compatibility principle.
So the purpose of the graph should drive how it's designed.
Got it.
Let's start with the classics, two-dimensional formats. We've already touched on line and bar graphs. What more is there to know about them?
So line graphs, as we said, are great at showing trends, how things change over time, or the relationship between two continuous variables. And research by Carswell and colleagues, Shaw and Zaks and Tversky all back this up. An interesting finding by Zaks and Tversky is that even if you only plot a few points and connect them, people still tend to interpret the data as continuous, like they fill in the gaps.
I remember that example they gave about connecting the average height for men and women, and people thinking it means something about how maleness affects height along that line.
Exactly, yeah. Our brains just automatically look for that connection.
Yeah.
But Shaw and Carpenter warned that this emphasis on trends and line graphs can be a problem when you have data with multiple lines representing different things. People can get so caught up in those basic relationships that they miss other important stuff in the data. There's a good example in Figure 3 where achievement test scores were plotted against noise level and then against room temperature. People focused mostly on what was on the x-axis.
Interesting. And how about bar graphs in those kinds of situations?
Bar graphs, as we've seen with the work of Carswell and Wickens, Shaw and Sachs and Tversky, are generally way better at showing those like individual comparisons between, different categories. And Shaw and Shellhammer found that they're less likely to bias how people interpret things compared to line graphs, especially with multivariate data. There's an example of this in Figure 4, which shows the same achievement test score data as before. People were more likely to consider both noise level and room temperature when it was a bar graph instead of a line graph.
So bar graphs for those quick comparisons.
Yeah.
Got it. What about some of the other 2D formats like pie charts and tables?
Right. So with pie charts, research by Simkin and Hasty, Coslin, and Wilkinson suggests that they're better than divided bar charts when you really want someone to understand proportions. This is probably because we're pretty good at visually comparing areas or angles.
Hmm.
However, Coslin points out that if you also need to show the actual numbers, not just the proportions, then divided bar charts might be a better choice,
Ah, okay.
even though they can make judging the proportions a bit harder.
Right, right.
And then tables. Well,
Yeah.
tables are the simplest. It's just rows and columns of data.
Yeah. They seem pretty, straightforward.
They are, and Guthrie and colleagues have actually shown that they're the best when you need to show those individual data points really accurately.
Hmm.
But the downside is they don't give you that integrated information. You see the numbers, but it's harder to see overall trends or relationships compared to a graph.
Right.
It really all comes back to what you want people to understand from the data. As Cleveland and McGill's research in Table I shows, using things like spatial extent or position along a common scale are generally the most accurate ways to represent quantities.
Okay. That gives us a good handle on the 2D formats. Now, what happens when we add another dimension? Three-dimensional displays seem to be everywhere these days.
Yeah, they really are, especially as computer graphics have gotten better. But the research on how well we actually understand them is still, kind of limited. Wickens and colleagues found that they could be good for tasks that involve integrating information across all three dimensions.
Okay.
And Shaw's work on wireframe graphs, like the one in Figure 5a, showed that people were more likely to think about the relationships between all three variables compared to when the same data was shown in a 2D line graph, like in Figure 5b.
So they might help us see the bigger picture with complex data.
Potentially, yeah. But there are some downsides. Research by Merwin and colleagues suggests that the perspective in 3D drawings can actually distort or hide important information. And in Shaw's study, people were less accurate at reading individual data points in those wireframe graphs, and said they were less familiar with how to understand them.
So 3D might be good for certain tasks, but it can also mess things up.
Exactly.
What about animation in graphs? I feel like that should be a really powerful tool for showing changes over time or complex relationships.
Yeah, you'd think so. And it's a common assumption that animation is great for showing complex stuff, especially things that change over time. But the research for using it in graphs specifically is actually pretty limited. A lot of the research is focused on, very specific applications for professionals like statisticians.
Mhm.
Becker and colleagues found some benefits for seeing 3D structure, and Marchark and Marchok saw some advantages for identifying clusters in 3D scatter plots. But that was in very specific situations.
Okay, but for just general graph reading.
Well, the overall consensus, even from people who use animation software, as reported by Huber and Skuzel, is that it can be really hard to accurately see and understand the relationships and trends shown through animation. And research on animation in other areas by folks like Hegarty and Morrison and their colleagues suggests that, the way we perceive animated stuff can be tricky and lead to mistakes. So while it might be good for some specific tasks, we need more research on animation and how it can be used effectively for people to really get graphs, maybe hold off on the fancy moving graphs unless you really know they help.
Got it. Let's move on to some other visual elements that graph designers can play with, like color.
Okay, so color can be really powerful in graph design. It can show quantitative information, like in heat maps, where different shades show different values.
Mm.
Or it can be used to, separate different categories or variables, like discussed by Brockman, Cleveland, and McGill, and Hoffman and colleagues. But Cleveland and McGill make it really clear that color isn't the best way to show precise quantitative data. And it can even be misleading if it's used for continuous data, as Phillips pointed out. We might think certain colors just mean more or less without realizing it.
But it must have some benefits for other parts of reading a graph, right?
Yeah, definitely. One big benefit, highlighted by Lewandowski and Spence and Koslin, is for grouping. Color helps us quickly see what data points belong together, like if you're showing different product lines on a sales graph. And Koslin also suggests that if you keep the same color for the same thing across different graphs, it can help people see those things as related. And then there's research by Brockman, Fisher, Koslin, and Schmid that suggests that using meaningful color choices, like red for hot or blue for cold, can help us remember what different lines or bars represent. This can be especially helpful for kids, as found by Halford and colleagues.
Yeah, so instead of constantly checking the legend, the color itself tells you what you're looking at.
Right, but the meaning of the color has to be clear and consistent, as Brockman pointed out, like how green might mean different things in finance versus healthcare.
Gotcha. So color is great for, like, keeping track of things, but it's not the best for showing exact numbers.
Exactly.
Okay, what about the decision to use a legend versus just directly labeling things on the graph?
That might seem small, but it can really change how easy a graph is to read. Legends make us keep information in our working memory, so we're constantly looking back and forth. This can increase what we call cognitive load, which basically means it makes our brains work harder.
Right.
Koslin explains this, and it's also shown in Figure 6b. So the general advice is to directly label the graph features, like in Figure 6a, especially when you want to keep things clear and easy to understand. This is even more important for kids who don't have as much working memory to spare.
Okay, so for clarity, especially when someone's learning, direct labels are the way to go. Now, what about that thing where people add a fake third dimension to a 2D graph? Like, those bars in a bar chart that have that, like,
Yeah.
fake sense of depth? Like in Figure 7? Why do people do that?
Yeah, those are called extraneous depth cues, and they're everywhere. In media, even textbooks, as Spence and Tufte observed. Tufte was really against them. He called it chart junk. And there is research, like by Fisher, Zaks, and their colleagues, that found people are a bit less accurate when they try to read exact data points or compare things precisely in those 3D displays compared to 2D.
But we still see them all the time, so there must be some reason people think they're good, right?
Yeah.
Even if it's just, like, aesthetic.
Well, other research, like by Carswell and Spence, has shown that there might not be a big difference in accuracy or speed when people are making more general comparisons, at least when they're going off memory. And Levy and colleagues actually found that some people just like how those 3D displays look better, so maybe they're not as bad as people thought, but they don't really add anything in terms of clarity.
So a bit of visual interest maybe, but be careful if you really want people to get the exact data.
Right.
Okay, last thing in our visual toolkit. Density of data points and the overall aspect ratio of the graph.
Yeah, those seemingly minor factors can actually subtly change how we see the data. So Cleveland and colleagues and Lauer and Post found that when data points and scatter plots are more crowded, either because there are more points or the graph is just smaller, we tend to overestimate how strong a correlation is. And Cleveland also says that the aspect ratio, the ratio of the height and width, can affect how easily we can see patterns. He suggests that an aspect ratio where the curves are close to a 45-degree angle is usually the best for spotting repeating patterns.
So even stuff like the size and shape of the graph can actually bias how we see the data. It's almost like the graph is, like, pushing us towards a certain interpretation before we even start thinking about it.
Exactly. And this leads to the next big piece of the puzzle,
Yeah.
our own brains and our knowledge about graphs themselves. It's not just about what's on the paper, it's also about what's happening in our heads.
Okay, so our experience and understanding of graphs come into play here. How does our existing knowledge about graphs, like the graph schemas we discussed earlier, affect how we understand new ones?
So just like we have mental models for other things in life, research by Schiano and Tversky and Schiano suggest we also have them for graphs and maps, these mental models can actually change how we remember graphs. For example, college students in their studies tended to remember lines and graphs as being closer to a 45-degree angle than they really were.
Interesting.
But here's the thing. When they were told the exact same image was a map of roads, they remembered the lines as being closer to horizontal or vertical.
Wow, so our brain has this, like, default idea for how graph lines should look,
Yeah.
and it changes our memory to fit that.
Exactly. And we also develop strong ideas about how graphs are usually set up. Like Gaddis and Holyoke found that people expect the variable that's being affected to be on the vertical y-axis and the variable that's doing the affecting to be on the x-axis. If a graph does it differently, people can misinterpret the slopes, thinking a steeper steeper line means faster change when it doesn't because the axes are flipped.
Right.
It shows how much we rely on these, basic conventions.
Yeah, and how we can get tripped up when something breaks those rules.
Exactly. And then younger kids, especially elementary school age, often make this mistake called the slope height confusion, as described by Bell and Janvier. They might think a steeper upward slope always means a higher value, not a faster rate of increase. They look at where the lines are at a certain point, not how fast they're going up or down.
So they haven't quite grasped, like, the whole idea of rate of change.
Right, yeah. And then in a 1995 study, Shaw found that college students who were new to graphs often misinterpreted independence.
Okay.
When shown a graph, like the example in Figure 8b, where two things didn't actually have a relationship, these students still assumed there was one. They relied on what they already knew or assumed about the topic, not on the actual data.
Ah,
For example, they might say, as the number of drunk drivers goes up, so does the number of car accidents, even when the graph didn't show that. But people who were experienced with graphs were better at seeing when there was no relationship.
that's fascinating. So even when we have the data visually, we can still interpret it based on what we already think, even if it's wrong.
Yeah, and this takes us to the next big factor,
Mhm.
content knowledge.
Right, the influence of what we already know.
Yeah, exactly. Like that drunk driver study showed, what we know or think we know about what the graph is about has a huge impact on how we understand it.
Shaw and Höfner talk about that classic study from 1979 by Lord and colleagues, where people were more critical of research that went against their beliefs,
Right.
especially about controversial topics. It seems like that tendency to like information that agrees with us also applies to how we see graphs.
Absolutely. And a bunch of studies have shown that our beliefs can really change how we estimate the strength of correlations between things. For example, research by Friedman and Smith and Jennings and colleagues found that if we already think two things are strongly related, like let's say height and weight, we tend to overestimate how strong that correlation actually is when we see it in a graph.
And it's not just about estimating relationships, right?
Yeah.
Our knowledge can also shape those more general interpretations of what a graph is showing.
Exactly. Shaw's more recent work has shown that people are more likely to make broader inferences about general trends when they're looking at graphs that show, familiar relationships.
Mm-hmm.
Like that car accident and drunk driving one we talked about, compared to graphs showing things that seem less related, like ice cream sales and fat content. And then Shaw and Shellhammer found that people who aren't as good at reading graphs have a tougher time figuring out those big picture trends.
So if we know a lot about the topic, it can actually help us see those bigger patterns.
Right. But it can also work against us, especially for younger learners like Bell and Janvier, Leinhart and colleagues and Priest have all pointed out. Kids in elementary school are really likely to do what's called iconic interpretation. They basically see graphs as literal pictures of things happening in the world, not as abstract representations of numbers and relationships.
Mm-hmm.
That race car speed graph example is perfect for this.
Yeah. It's like they need to learn that the graph is a code, not a literal picture.
Exactly. And how hard a graph is to understand can also depend on what kind of information it's showing. Clement's research, which Leinhart and her team cite, suggests that graphs showing acceleration are the hardest for students to get, then velocity, and then distance or position. And trying to go from one type of graph to another, like from velocity time to distance time, is also tricky. Interestingly, though, time as a dimension seems to be easier for students, maybe because so much of what they learn involves things changing over time, like Leinhart and her team suggest.
So how familiar we are with the ideas and the dimensions in the graph really matters.
Absolutely. And the big concern here, as pointed out by research from Hunter and his colleagues and Lehrer and Romberg, is that for people who are new to graphs, especially in science and social science, what they already know can sometimes overpower the actual data in the graph. This becomes a problem when they need to really critically evaluate the information. We have to be able to see the data for what it is, even if it goes against what we thought was true.
That's such a good point. We've covered so much here today about how graphs actually work. Can we maybe distill that down into some practical advice? Like, what are some things we can do as learners to be better at both looking at and creating graphs?
Okay, so when it comes to choosing the right graph format, the main thing is to think about what you want to say. Line graphs are usually best for trends or continuous variables. Bar graphs are great for comparing different categories. Pie charts are good for showing parts of a whole, especially proportions. And divided bar charts can be good if you need to show both proportions and the actual numbers. The implications for data display section in Shaw and Huffner's paper has a good breakdown of this.
And for those really complex data sets, could it be helpful to show the data in a few different ways?
Yeah, absolutely. Like showing the same data in a table and a line graph. That way people can see both the exact numbers and the overall trends. It can lead to a better understanding and also help build those graph schemas we talked about.
You mentioned earlier that we should use the best visual ways to show quantitative information. Can you remind us what those are?
Right, so based on Cleveland and McGill's research, the best way is to use position along a common scale, like in bar charts and line graphs. Then it's position along different scales, then length, direction, and angle. So basically, stick with bar and line graphs when you really want to make quantitative information clear.
Got it. And what about animation? Should we still be careful about using it in graphs?
Yeah, I'd say be cautious. Unless there's a really clear benefit for a very specific task, animated graphs might not be that helpful for general understanding. They might even be more distracting.
Okay, good to know. What about ways to minimize that cognitive load we talked about, to make graphs easier on the brain?
That's super important. Use colors and symbols that are easy to understand and try to directly label stuff on the graph instead of relying on a legend. Keep individual graphs simple and focused. Don't try to put too much on one graph.
Makes sense. And for color, any best practices there?
Yeah, when using color to separate categories, pick colors that are really different from each other to make them easy to tell apart. And if you need to show continuous data with color, like a heat map, use changes in how bright or saturated a single color is. But always remember, for comparing actual numbers, spatial extent, like how long a bar is way more reliable than color.
Okay, what about that whole 3D thing? Should we just stick with 2D graphs if we want people to get it right?
3D effects might look cool and they might not always hurt basic understanding, but if you really want people to get the exact data and make precise comparisons, 2D graphs are definitely the safer way to go.
What about the scale and shape of the graph?
Absolutely. Be aware of how the aspect ratio, the height and width, and how dense the data points are, especially in scatter plots, can change how people see patterns and correlations.
Mhm.
So choose scales and dimensions that accurately show the data without, exaggerating or downplaying any relationships.
Okay, last thing. That connection between the graph and any text that goes with it.
Right. So what we want is what we can call text graph harmony.
Okay.
Basically, make sure the text matches what the graph shows, especially when you're explaining it to someone who might not know a lot about the topic. This can help them understand it correctly, especially if the data might challenge what they already believe. Pointing out specific data points or trends in the text can also really help.
Those are all really helpful tips. Now, thinking more about us as learners, what can we do to be better at understanding graphs? Based on what Shaw and Huffner say in their section on implications for teaching graphical literacy.
First, practice reading graphs in the context of what you're actually studying. Remember that in fields like science and social science, graphs aren't just there to show information. They're tools for analysis and making judgments, especially in areas where our biases and our real-world knowledge can affect what we see.
So really engage with the graph, like it's part of the thinking process.
Exactly. Second, practice changing data from one format to another. Like if you have a table, try drawing it as a bar graph or a line graph.
Oh.
Or if you see a graph, try to imagine it as a table. This can really help you understand how different visuals map onto the data.
It's like you're learning to speak the language of graphs more fluently.
Yes, exactly. Third, when you look at a graph, really focus on connecting what you see with what it means.
Okay.
Don't just see a line going up. Think about what that upward slope means for the variables. What does the height of a bar represent? What does a pie slice tell you?
So actively decode what the graph is saying.
Yes. And finally, be critical and question things when you read a graph. See it as a task of interpretation, not just finding facts.
No.
Ask yourself, what's the main story here? Does it match what I already know? Are there other ways to see this data based on how it's shown?
So be active, ask questions, consider different views. Don't just accept the information as it is. That's great advice. Before we wrap up, can you give us a quick recap of the most important things about understanding graphs?
Sure. We've learned that understanding graphs isn't just about seeing the information. It's also about interpreting those visual relationships and connecting them to what we already know.
Right.
Effective graph reading depends on both the graph's design and our own skills.
And on that note, here's our final thought for you, our listener. Now that you know more about all the little things that go into graph design and how we understand them, we challenge you to look at visual data with a more critical eye. What assumptions might you have been making without realizing it?
We hope you'll now pay more attention to the graphs you encounter. Think about the design choices and how they might affect you. Have you ever misinterpreted a graph or seen someone else do it because of?